So the goals of the NCCR SPIN is to build a quantum computer.
In this program we focus on one particular platform, a silicon germanium spin qubits.
And there's lots of things to be done because we have to figure out what is the right material, what is the right spin qubit.
But also the algorithms, the error correction schemes, and the first applications of quantum computing.
We are now on a very steep path towards that goal, and there are many challenges, and we want to address these challenges in this focused area. The collaborative aspect is extremely important because this field of quantum computing is very broad-based. So there are many different disciplines which come in.
You effectively become a bigger team when you work together with the theorists who think about understanding your data or who give you ideas what to measure in the first place, but also work together with the material scientists.
The general challenges for quantum computing are at a technical level. The quality of qubits have to be higher, their fidelities have to be closer to 100%, their interoperability has to be more streamlined and so-called scalable.
Putting multiple qubits in an integrated way is not a trivial issue.
The things we are working with are really fragile and especially vulnerable to environmental fluctuations.
The biggest challenges are usually errors and error corrections, and this can be done through advancing the quality of materials, advancing the quality of fabrication, but also advancing the computation algorithms.
There is still a lot to do in terms of research and optimization of the core elements in order to get to the point where scaling will be easy.
To me, the most rewarding part of my work is sharing something with a community and then seeing there's a push towards it and then seeing more and more people working on it.
My motivation to work on quantum computing is to be working with the pioneers of a new technology that is being developed.
Great rewarding part is really to be participating in something bigger. Here you have a project that has a clean objective.
Quantum computing is one of the most ambitious goal of us as humanity.
It's comparable to something like nuclear fusion or like space technology.
It makes us confront very fundamental points of physics and of how physics, modern physics, quantum physics can be applied to situations in the world. But also it has an ending point which is quite fantastic, you know, that it's like building the next particle accelerator, and really truly in complexity it is something of that scale.
What's exciting about quantum computing is the promise of changing the way we address so many problems.
If it comes one day, of course it would have impact on many areas of our lives.
Whether it's for medicine, whether it's for new types of materials, whether it's for other complex optimization problems.
There is really big hope that we can do like quantum simulation, that means like simulation of the world which is much more accurate.
We've seen it with all the big industrial revolutions throughout history. Every time there is this big industrial revolution, life changes completely, and I think it's going to be something similar to that.
Probably the most exciting things are those which I can't think of today because the computational power will be very large, so I'm sure we can do also those things. I'm looking forward.